Hello there. First of all, allow me to introduce myself. My name is Rui Frasos Garcia. I am from the Electrics and Electronics Department from the Faculty of Engineering in the University of Indonesia, and today I'm going to explain about potential energy. Now, what is potential energy? Well, potential energy, by its base definition, is an energy held by an object due to its position relative to other objects. Now, but what does that actually mean? Well, since it is a potential, it is something that is held inside the object until it is subject to change. And when it is subject to change, that energy is able to be transformed into other forms of energy. Since we know that energy cannot be created or destroyed, it can only be changed. Most of the time, energy is changed from this potential energy stored inside the object. Now, there are four basic forms of potential energy that we see on a daily basis. Those four are the gravitational potential energy, elastic potential energy, magnetic potential energy, and lastly, electric potential energy. But since we are in the mechanical physics class, I'm going to mainly discuss about the gravitational potential energy and the elastic potential energy. Now, before we go further and break down the definitions of these two and determine the formula and the equation needed to calculate the potential energy of an object due to these two potential energy positions, there is one more key feature that we have to discuss in order to break down this equation even further and figure out the value of a potential energy inside an object. And that key feature is work. Now, work in physics is not like you going to your job and filling up your quotas by doing assignments. No. In physics, work is the measure of energy transfer that occurs when an object is moved a certain distance by an external force. And those two are the main features of work. There needs to be distance and there needs to be an external force acting upon the object. Now, based on this definition, we can kind of imagine what the formula or the equation of work is, right? Since it is based on distance and external force, the base equation or formula for work can be described as W is equal to F times S, or work is equal to the force exerted on the object multiplied by the distance that it is traveled. Now, what is the correlation between those two? Why am I discussing work when we're clearly discussing about potential energy? Well, there's actually a lot of similarities, and work is really just an example of the change of potential energy that is in the most basic form. Now, when we look at work, we're actually looking at the amount of energy exerted from the object. Now, since I already said before that energy cannot be created or destroyed, this energy that comes because there's work needs to come from somewhere, right? And that somewhere is most of the time potential energy. Now we can clearly see here, and we can actually calculate it if we see that it's actually the same due to the axiom of it alone. We can clearly see that delta U here, or the change in potential energy, can be equal to the negative of work. Now, why is it the negative of work? Why isn't it the same as work, since it's only changing, right? Well, let's take an example of a ball. In this example, like you can see in the picture on the right here, the ball is going to be thrown up and it's going to fall back down on its own. Now, why is that happening? We all know this. I mean, we experience it every day. It is because there's a gravitational force from the earth pulling the ball down. Now, when the ball is going from the apex, it will stop there for a while. If you look at it very closely, if the ball reaches the apex of its elevation, it will actually stop a while before it goes back down. Now, when it's doing that, it is actually storing up potential energy. And potential energy is actually being held up there, and when the force exerted is zero, the initial force that it needs to throw that ball that high is zero, it will go back down. And we can calculate the potential energy of that ball when it's high up by the amount of work it has done by going from the top, hitting back down to the ground. And since the direction is negative, and the height is negative, the s is negative, since it's going from a higher place to a lower place, that's the reason why the w is negative, because the energy needs to be positive. Now, before we go even further, we need to discuss about the forces that are acting up on an object, because there are mainly two types of forces, and one of them can work here for one of them won't be used, and we need to know the difference. Those two are conservative and non-conservative forces. Now, what are those? What does conservative force mean, and what does non-conservative force mean? Well, conservative force basically means the force that is acting up on the object will only change the object into a certain type of energy, and it will turn it back to that other type of energy. Now let's just take an example of the ball thrown earlier. That's such a basic example, and we can apply it here too. When that ball is thrown up, we are assuming that there is no interference between the forces of the ball going up and while the ball is going down. That happens on a conservative force basis. What it means is that the ball is only going to change from kinetic energy to potential energy, and from potential energy to kinetic energy. This type of force is something we typically use in the basics physics class. Compare that against to non-conservative energy. The example of this, we can also take it from the falling ball. If we add in something that we all know called friction into the equation, the ball will not have the same energy as it would from when it's going up as when it is going down. And that is only due to the friction. And since we know that the energy cannot be transformed, or it cannot be destroyed or created, where's that energy going to? Well, the energy is actually turning into thermal energy due to the friction of the object and the air. If we're taking an example of the ball, this can be proven by when you rub your hands together, there will actually be heat created because the forces that you are exerting, some of that is turning into thermal energy and causing the object to heat up. Now, we can, since we are in a basics physics class and we're dealing with basic numbers, we are going to assume that most of the questions given to us we're doing in a conservative force form, since non-conservative force form is basically something for more advanced calculations, and we need a lot of assumptions to confirm that number. Since we won't know how much energy is going to be transferred. So we're going to assume that is a conservative force. But what if you are asked to prove that it is a conservative force or not? Well, to look and see whether or not an object has a conservative or a non-conservative force applied to it, we can just look at the axiom right here, where the net work done by a conservative force on a particle moving in any closed path needs to be zero. Meaning that the object, all the forces when totaled up, all the work when totaled up, done by the force, needs to be zero. But there's an interesting point here that we all need to know the definition of, and that is a closed path. What does a closed path mean? Well, a closed path basically implies that the object is going from one point to any point. Doesn't matter, as long as from any of those points it goes back to the original point, that it will be a closed path. Basically, when we're imagining it, just imagine that there's a shape, and that shape needs to be closed all the way. That is what a closed path means. So let's just look at the picture down below. From A to B, the network needs to be zero from those forces going from the work done from point A to B, which is the first one, which is labeled 1, and from B to A, which is labeled 2. When work 1 plus and work 2 are added, they need to be 0. Now, it doesn't matter which route it takes. If it is a conservative force, it will be 0. It can go all the way around the screen to go to B and then just take a straight line from B to A. And if the network is 0, it will still be a conservative force. Now, since we got all of that out of the way, let's go back to the main topic, which is potential energy. Now, since we already know the equation and the proof before that the change in potential energy is equal to negative of work, whereas work we can already know the definition of is force times the distance traveled, right? Well, the definition here is actually still the same. Well, we're just basically making an integral of the force, assuming that it has an element of x to it. When you integral it, it will still be force times the distance. But since we have to assume that there's a lot of forces happening at the same time, we're gonna put it as F, and then we're gonna define it later whether or not it's going to be gravitational, elastic, magnetic, or electric. And when we combine that together, we can see that the change of change of potential energy is equal to the negative of integral from x2 to x1 of the F element of x, the integral integrated by x. And when we apply that to a gravitational position, which we can see here, I just basically replace all the x's with y's to prove that since gravitational energy basically has the difference in height, is basically what is most commonly used. That when there is a different height, it will have a different potential energy, and this is the proof. Since gravitational energies, we can, if you remember, in the first times the lessons have been conducted, we know that gravitational force is equated to the mass times the gravitational speed of that point. So, done by the basic calculations, we can know that the potential energy in the basis of gravity, or the gravitational potential energy, is equal to the mass of the object times the gravitational acceleration at that point at the time times the height of the object. And since we are also going to tackle elastic potential energy, here is the formula. We just basically change the force from gravitational force into a force basically done by a spring, since elastic in physics, elasticity usually goes back to springs, which is the most common type of elastic object. We can just enter it in the equation. We know that the force done by a spring is the constant of the spring times the change of distance from the equilibrium point, or negative k times x. And after calculating it, we can know that the potential energy in an elastic object is equal to half times its constant times the change of distance from the equilibrium point squared. And that is all for potential energy discussion today. Next we're going to discuss about the conservation of mechanical energy, and it is going to be discussed by my friend Kivlan.
So let's move on to another topic, which is the conservation of mechanical energy. So we know that we know what is potential energy and we know what is kinetic energy. So we now continue on to mechanical energy and its principle of conservation. Now let's start off with what is mechanical energy. So mechanical energy is the sum of its potential energy and the kinetic energy of the objects within it. So basically, the combination of the potential energy that is in that state and the kinetic energy that it is doing basically in that same state. Combined, the sum of that equals its mechanical energy. Now, Uh, since mechanical energy is that, we're going to focus more on the conservation of mechanical energy. So, and also to demonstrate the principle a lot more clearer, we're going to assume that only conservative forces work on this, ideal world, on this system. Why? Because conservation of mechanical energy doesn't really work if there is non-conservative forces. Now, what is a conservative force? What is a non-conservative force? Basically, a conservative force is basically a force that cause energy transfers within objects within said system directly. Now, non-conservative forces is energy transfers that dissipates energy outside the system. For example, air resistance or airflow and drag, friction, all of this is non-conservative forces. These forces grab energy from the system and release it or dissipate it into other systems or the world or to the bigger system. So to make it easier and to make calculations simple and to really show the conservation of mechanical energy, we'll only assume that in this ideal world there's only conservative forces. Now, conservation of mechanical energy. We're gonna start off with, we've already learned that when a conservative force does work on an object, the amount of work it does is equal to the amount of change that has happened to said kinetic energy. Because what work does, it basically transfers potential energy that the object has into kinetic energy. Now, because of that, we can say the same thing about potential energy. You can see here that for kinetic energy, we said that the difference in kinetic energy between two states is the amount of work, and the negative value of the amount of work is equal to the amount of change in the potential energy, because it's just transfers between kinetic energy and potential energy. Now, with this in mind, we can turn it around into this equation, which states that the potential energy and the kinetic energy of an object in a state will stay the same in another state. Uh, in itself, it may be different. For example, the kinetic energy may increase while the potential energy may decrease. In one state and in the other will be different. But the combination, the sum of both of these energy will stay the same. Now, uh, you now know why we only have conservative forces. It's because if we have non-conservative forces in in the system, the amount of mechanical energy that the object has may decrease because of drag, air resistance, friction, because the mechanical energy that they have will get dissipated because of friction or because of non-conservative forces. But if we don't have that, we can use this equation to calculate a lot of things, really. It will make things more simpler than just using Newton's law. Uh, to simplify this even more, in words, it basically means that the mechanical energy of an object stays the same no matter what state it's in. If it's falling, the mechanical energy will stay the same still as when it is running 1,000,000 kilometers per hour. It doesn't matter as long as there's no conservative forces acting on it, and um, actually, yeah, and that's it. Only no conservative forces acting on it. The mechanical energy of an object stays the same no matter what state it's in. If it's falling, if it's running, if it's not moving, it will stay the same. Now, all of this is excellently described, exemplified in a pendulum. In this part right here, I'll use my mouse. We have some kind of repeated motion, okay? A simple pendulum, basically. Now, in the first step, we'll start right here. The pendulum goes. Actually, let's not start here. Let's start, like, for example, let's start right here. We are holding the pendulum, for example, and then we're about to release it. At this point, since we assume that there's no air resistance and whatever, we assume that there is no kinetic energy because, for example, it's not moving in this example. So that means, in the latest equation, which is this, since it must stay the same for the mechanical energy, we can say that there is all of it, all of the mechanical energy is the same as the potential energy. We can even calculate it later by just doing the distance and whatnot. But basically, at this point in time, the amount of potential energy is a lot, and the amount of kinetic energy is 0. And the amount of potential energy is equal to the amount of mechanical energy because of that. Now, we release it. When we release it, there is some amount of speed. It's not at the max speed. There's still some amount, but there's still some amount of speed. And there's still some amount of height here before it reaches to the state where it's 0. And because of that, there is a shared amount of potential energy and kinetic energy. So there's some amount of potential energy, some amount of kinetic energy, combine this, and we have the same mechanical energy. So in this point and in this point, it's still the same mechanical energy. For example, this is like 5 joules. This is still 5 joules. But in this case, the 5 joules is equal to the 5 joules in the potential energy. In this, it might be different. For example, it's only 2 or 3, it's 2.5 joules. But no matter what, the total of the issue will always be 5. Now in here, this is where it reaches its breaking point, where it reaches the maximum amount of speed. And because of this, there's no potential energy. It reaches its 0 height and its max speed. And because of this, there is tons of kinetic energy and no potential energy. Because of this, the amount of kinetic energy is equal to the amount of mechanical energy. And this goes on, repeated, everything stays the same. All of this, from here to here to here to here, it has 5 or whatever amount of joule you have. It stays constant. The total energy in all of this does not change. Now, let's move on to reading a potential energy curve. This is we can say as an example, really, when there's an object, for example, that is being acted on by a one-dimensional conservative force. It's really specific, but it helps a lot in understanding what potential energy is and what it basically does. So let's learn at least about how to read a potential energy curve. Now, since we have a highly specific scenario here, which is an object that is being acted on by a one-dimensional conservative force, we can say that the work that is being done can be defined as this. We already mentioned this equation right here, but we specified this part again to the equation of work, which is the amount of force that is being acted on by the object times the amount of distance traveled. And this is basically it, right? So the amount of potential energy it has is this. Now, we'll plot the amount of potential energy in the object to make it more simpler. So this is it, right? This is the plot of the potential energy of said object against the position it's currently is. For example, like 2 meters, 4 meters, or something. I don't know. Basically, this is just an example, right? So because this is like and also let me go back a bit. Because this equation is like this, we can actually revert it around to finding the amount of force that the object has to find basically the force. We can use derivative, basically the derivative of the function of potential energy divided against the position. So basically in here, the derivative, the slope of this is equal to the amount of force. You can see right here near x1, the amount of slope is deep, is going down right here. There's a lot. And then when it reaches x2, it reaches 0. When it reaches x3, which is a high slope, it goes back, no, it goes 0. When it goes back down, it goes back down as well. Basically, the derivative of this plot translates to the force because of this equation. Now, we got this two plot now. This is the force, this is the potential energy, and both of these are against the position. We can now find the on how to basically read it and how to find actually the kinetic energy from just the potential energy. So let's just say that we have the object has a 5 joule mechanical energy. Now when it starts moving, right? When it starts moving, in here we can calculate like what basically is happening to the object by just looking at the plot. In here we see that the amount of mechanical energy is same as the amount of potential energy, which means that the object is not moving. And because of that, we can also state that in here, when there's 0, we can state that there's a huge amount of kinetic energy and it is going as fast as it can, like high amount of speed, high amount of velocity. And here we have some amount of potential energy and some amount of kinetic energy. So it's moving, but not as much as it was at the position x2. And this is basically how you read a potential energy curve and how to understand how the object, at what state the object is in, what it's doing, what's the velocity and whatnot. By reading this, we can understand the object's state. Now, if you continue, as you can see, this already explained, K is a zero turning point. So basically, at this point right here, the object cannot go anywhere. Why? Because it only has potential energy. There's no velocity, 0. It cannot move. But however, in here, when it starts to move, there's so much kinetic energy, no potential energy, that is moving the fastest, the huge amount of velocity. And in here is just some amount of kinetic energy and some amount of potential energy. Well, there's mostly potential energy. But yeah. Now in here, it is now in here. This is basically an example. Here we set the mechanical energy into 5 joules. But if we go here and just set it to, for example, like here, voltjoules, like this purple line here, it'll get stuck at x5. While in here, it'll get stuck at like between x4 and x5. And if we set it to 1, it'll stuck at x4 and won't go anywhere past that. It cannot escape left or right. Where in here with x5, it won't get stuck like at all. It will keep moving because there's still 1 kinetic joule, but if it's 4, it'll get stuck here. If it's 1, it'll get stuck here, and so on.
Hello guys, my name is Ilham Harahab, and this is work done on a system by an external force. Let me tell you something about um, force. Force is a reaction when you do something. So an external force means something from outside, other than from the system. Now the key idea is here, if you see work is energy transferred to or from a system by means of an external force acting on system. So is the transfer of energy means work done. Now the second key idea is the when more than one force acts on system, the network is the transferred energy. So when object is stationary, that means there is equal force on all on all act of them on all act. Therefore, there is no network. There is um, equal work on all sides. When friction is not involved, the work done on the system and the change delta energy mechanic in the mechanical energy of the system are equal. As you can see, the work done is equal to mechanical energy and delta K plus delta U. Another key idea is when a kinetic fractional force acts within the system, then the thermal energy of the system changes. As you can see, the energy is associated with the random motion of atoms and molecules in the system. This is the formula when work is done in the system. Another key idea is that the change in energy is related to magnitude of the fractional force. Therefore, the formula is this. Now we go to the next one. If you see here, uh, let me just read it out for you. Work done on the system by an external force. As defined in chapter 7, we previously learned about this. When being energy, work is a energy transfer to or from an object by means of a force acting on an object. Now, in this presentation, we're going to extend it by external force. As you can see here, when work done into the system, it's a positive work. And when the work is taken from the system, that means is negative. Or you can see here, the negative means that transfer from the system and transfer of energy to the system. The energy statement for such transfer is the work kinetic energy theorem of equation this delta K is equal to work. A single particle has only one energy account called kinetic energy. External forces can transfer energy into or out of that count. And if in real world, there is not only kinetic energy and work done, but there is also potential energy when it's stationary. And it's more complicated, as you can see, because there is multiple energy counted. Well, let's see two basic no we have two ways of explaining this. One is when there is no friction involved. That means that we can have it as conserved. if you look at this equation here, the work done and means that change in energy, change in kinetic energy is the same as the I mean the work done is equal to change in kinetic and change in potential, gravitational potential energy. That means there is no other system is involved in this equation, which means it's conserved. But in reality, there is a friction, a tiny bit friction, that is causing this equation not balance, not equally. And that goes to this equation here. Force minus force K is equal to mass times acceleration. What happened is that when the gravitational potential energy occurred, it actually goes through frictions such as air resistance and such on. If you look at another example here, when the work is done on a sliding, when someone's sliding, go on a slide, there is a friction, and that occurs. That means when the work is done, it should be less because of the friction. That means that it's not equal to the work done, which is the mechanical energy is not equal to the work done here. Now, if you look at this example next, there's a picture below. Consider the constant horizontal force pulls a block along an x-axis and through a displacement magnitude d, increasing the block's velocity from phi to phi 0 to phi. That means there is a change in velocity, and therefore there is a constant kinetic fractional force from the floor. This is the system. What happened? The applied force supplies energy. The frictional force transfers some of its thermal energy. So the work done by the applied force goes into the kinetic energy and also thermal energy, because the friction produces heat from that. Not all of this friction, this work done here goes through mechanic energy. It can go through, name it like a heat, and probably gravitational potential, but there is no change in heights. So I think it's what I can name is mechanical and thermal energy, as you can see here. To explain this figure A, as you can see, a block is pulled across the floor by force. That means the force of friction is the opposite of the force, the directions moving. That means when it's going this way, the force is actually going that way, as you can see here. When it's moving that way, there is no constant movement of speed. When something is moving, it can go like really fast and then slow down. Not like stop like that. No, because then you would have like stopping uh, something to stop that. That also goes as the friction itself. Therefore, this change in speed also causes the work done more. Now, let me just explain about this change in motion, because um, the force are constant in this system. That means the acceleration is also constant. Even though the speed is changing, then we can find that acceleration. Now, when we substitute it into the equation, we have this equation here. And also, because the kinetic energy is equal to change in kinetic, we have more a general term for this. And when we talk about the change in potential energy, when it happens, it goes like, because the potential energy occurs when there's a change in height. Therefore, when something goes up a ramp like that, there is a change in height, right? When this occurs, then we can have this. We can have that equation down the line. Therefore, then through experiment, we we uh, we find that the increase of thermal energy is equal to the product of the magnitudes of the force of kinetic. I mean friction. Therefore, we can conclude that when a friction occurs in the system, friction could mean that there is external energy occurred as well. We can say that mechanical is on the line and heat energy equal to work done. Therefore, when an external force is occurred in the system, the result means that the work done.
Okay, so now we're going to continue our discussion on the conservation of energy. As we've discussed earlier, we've seen how energy can be transferred to or from objects and systems. In each situation, we assume that the energy that was involved could always be accounted for, which means energy itself cannot be created or energy itself cannot be destroyed. In other words, we assume that energy obeys a law called the law of conservation of energy, which is concerned with the total energy E of a system. That total is the sum of the system's mechanical energy, thermal energy, and any type of internal energy. So, what does this law state? What is the law of conservation of energy? The law of conservation of energy states that the total energy E of a system can only change by amounts of energy that are transferred to or from the system. Therefore, we can see that W, or work done, is equivalent to the total change of energy in a system, which translates to the sum of mechanical energy of a system plus the change in the thermal energy of the system and the change of internal energy in the system. Also, we can see that in the mechanical energy, it's included the changes of kinetic energy and the changes in potential energy such as elastic or gravitational or any other types of energy, just as my friend Rui has mentioned before. So now, what is an isolated system? A system is known to be isolated from its environment when there can be no energy transfers to or from it. Therefore, the law of conservation of energy states that the total energy of an isolated system cannot change. What does that mean? In an isolated system, we can relate the total energy at one instant to the total energy at another instant without considering the energies at intermediate times. That translates to we've seen how energy cannot be created or energy cannot be stored. Energy cannot be destroyed. In an isolated system, we see how the total change of energy is equal to zero. Therefore, we can say that mechanical energy added with the thermal energy added with the internal energy equals to zero. We can also let the mechanical energy equals to the mechanical energy before, say, a certain process has occurred minus a cert after a certain process has occurred, which becomes the change of mechanical energy equals the change mechanical energy after a certain process has occurred minus the mechanical energy before a certain process has occurred. Therefore, we can get the equation as seen below. So, for example, say we have an isolated system consisting of a rock climber, his gear, and the earth. As he rappels down the rock, he's changing the configuration of the system. He needs to control the transfer of energy from the gravitational potential energy of the system, because as we know, that energy cannot just disappear. Some of it is transferred to his kinetic energy. However, he obviously does not want very much transferred to that type, or he'll be moving too quickly. Therefore, he has this rope wrapped around him, which produces friction between the rope and the rings as he moves down. As he moves down, we can feel that there's heat around the rope and around the metal rings. Therefore, we can see how the gravitational potential energy is being transferred to both kinetic energy and thermal energy. Thus, the total energy of the climber, gear, and earth system does not change during his descent. Now, what happens if there are external forces acting on, say, a system? An external force can change the kinetic energy or potential energy of an object without doing work on the object. That is, without transferring energy to the object. Instead, the force is responsible for transfers of energy from one type to another inside the object. Look at this figure below. There's this girl who's holding the rail of in an ice skating ring. And initially, she's stationary, which means she's not moving. But as she pushes away from a railing and slides over the ice, her kinetic energy increases because of an external force, F, on her from the rail. However, this force does not transfer energy from the rail to her. Thus, the force does no work. As she's moving, we can see that she starts to change in her velocity. She begins to gain velocity. Her kinetic energy increases as a result of internal transfers from biochemical energy in her muscles, not from the force exerted. Therefore, an external force does not give out work. Another example seen from this car. A car has an engine, and this engine increases the speed of a car. During the acceleration, the engine causes the tires to push backward on the road surface. This push produces frictional forces that act on each tire in the forward direction. Therefore, we can see a net external force F from the road. This accelerates the car, increasing its kinetic energy. However, F does not transfer energy from the road to the car and does no work on the car. Rather, the car's kinetic energy increases as a result of internal transfers from energy stored in the fuel. Therefore, we can see that in both cases, sometimes the external force on an object can relate to the change in the object's mechanical energy if we can simplify the situation. Consider again the ice skater's example. During her push through distance d, we can simplify by assuming that the acceleration is constant, her speed changing from VO equals 0, or initial, which is her stationary, to V. After the push, we can simplify the skater as being a particle and neglect the fact that the exertions of her muscles have increased the thermal energy in her muscles and changed other physiological features that we can apply. Therefore, we get to see how the change of kinetic energy is equivalent or equal to the force multiplied by the distance moved. Or in other words, the kinetic energy, the final kinetic energy minus the initial kinetic energy equals to the force, in the x direction, which is F cos theta, multiplied by its distance moved. If the situation also involves a change in the elevation of an object, we can include the change delta U, or gravitational potential energy, by writing delta U plus delta K equals to force times distance cos theta. Now, what is power? Power, P, is the rate at which energy is transferred by a force from one type to another. Now that we have seen how energy can be transferred from one type to another, we can expand the definition of power itself. Power can also be defined as the rate at which work is done by a force. If an amount of energy E is transferred in an amount of time, the average power due to its force is, as seen in this equation below, P average, or the power, equals to delta energy over delta T, or the total time.